So the first problem is here. We're looking at the number, we're looking at the equation like so, like this. And we know how to solve this equation, right? It's like it's the roots of a complex number. It's an nth root of a complex number, nth root of a unity. Here I made this solution available for us. So WS, sorry, it's not WS, it's omega sub S. Omega sub S, that's the all possible solutions to these equations, and we did it like already 10 times at least. So you know how they're supposed to look. They look like this, and all together you have n possible solutions. Normally, I index them from 0 up to n take 1. Geometrically, I gave you a picture here of these solutions. I could not possibly give you a picture of arbitrary n, so I chose one n just for demonstration purposes. So I chose n equals 7 here, and that's the graph of those solutions. So I just gave you a few solutions here. This is W naught solution, the easiest one, the most trivial one, just identity. I think there are a few others. So this is the W1, and the one which is right before the W1 will be, I keep saying W1, but in fact that's a letter which is Greek letter omega. I'll fix myself. Anyway, so we're looking at these solutions, and the question, I don't remember what number of that question in yellow book, but if you look for the questions you will spot it very quickly. The question is, let's just see what happens if I sum up all of them, one after the other, and raise them to the power k. We need to find this a number. In fact, if you find the question, I think the question even gives you some hint what the sum will be. I think it says the sum will be 0 most of the time, but you have to identify for which case this sum will be 0. Right, it's a nice question. It's very, I mean, the solution itself is very short and simple, but it just spins around a very great idea about the complex numbers. And I'll show you this idea in a second, but first I want to ask you, what do you think we should do in this question? Here we go. What I suggest we do is this. We take my A, and I multiply my A by omega 1k. That's the very first root here, that's the one here, this one. So I take my A, the whole thing, and I multiply this A by the extra factor like this. And I just want to see what happens if I do that. Well, if I do that, look what happens. Obviously, if I take this extra factor and I multiply each term in this sum by this factor, all of them in the raised to the power k, I can group them together. So if I do that, it's here. The grouping will be looking like this. Here it is. You go on in this way. All of the terms here, which concealed by dots, you do the same thing. I think I showed you here the one which is before the last one. So the one which sits here, before this plus. Omega 1 times omega n take 2 to the power k, and the last one will be omega 1 times omega sub n take 1 to the power k. So far nothing interesting happened, we just multiplied, but now we can look at these numbers, and see what happens with these numbers. If I multiply omega 1 by omega naught, it will be just omega 1. What happens if I go for, I think here, for omega 2? Well, you can do it in exponential form, right? For instance, omega 1 is a number like this. That's the one here when s is taken to be 1. That's the one here where s is taken to be 1. Another omega 1 will be now the exponential like so. 2 exponentials like so. When you multiply 2 exponentials like so, you know how to multiply exponentials. You just add up the exponents expression. If I add them up, I skip a few arithmetic steps. If you add them up, it will be the 2 pi on n here, plus another 2 pi on n. Together will deliver 4 pi on n. Or it will deliver omega number with s being 2. So in fact, you will end up with this one, with this root. Next one in the row. Now, let me ask you this. Do you see some pattern in this behavior? What will happen if I multiply any middle omega in this one by omega 1? What will happen with that middle omega sub s? It will get like it will jump to the next one, right? Next in a row. Or you can just say it in these terms. When you multiply every vector in this representation by omega 1, the picture gets spinned or rotated by one step forward, right? Formally, you can justify it like this. Formally, you justify it like this. You multiply omega 1 by some middle one, by some omega sub s. You use your exponential forms for that. That's the exponential form for omega 1. This is the exponential form for omega sub s. right? So they all come from here, from my expression for the roots. And now you do your exponential multiplication. You add up the exponents. And when you add up these exponents, you end up with the exponent like this. And that's the exponent, that's the omega next in a row, the next omega in your chain of solutions. This is the omega sub s plus 1. So this geometrical observation, formally, that's the way how we formally present this. And now let's just now make this modification to this whole line we started with, this line. So if I do these modifications here, we end up with omega 1 to the power k, right? That's the one which stands for this bracket. Next one. Next go omega 2 to the power k, that's the one which stands for this bracket. Next one will be omega sub 3 to the power k. It's no longer present, I put the dots. What will go in the place of this term? Omega sub n take 1. Yes, that's true, to the power k. What happens in this term? Omega 0. You look close now, because this one, when you spin your picture forward by 2 pi on n, this omega n take 1 will be omega n, which is actually just omega naught, this one. And so you end up with this. What does it look like, this whole expression? It looks like A. Yes, it looks like A. Look how interesting, what kind of interesting conclusion we come up with. We multiply my A here on the left-hand side with omega 1 to the power k, and we come up with A again. It's here. So we're looking at the equation like this. A times omega 1 sub omega 1 to the power k equal A. Normally, if you think about of your A as an unknown, and you think about your omega 1k as an unknown, like an equation, then this only might happen on 2 occasions. You either have that this factor k, omega 1 to the power k equal 1, or you have, let me just zoom out a little bit and lift it up. Let's see if I can find it. Or you have A equals 0. I think I have a little or here for you. And now the final step of the solution, or final step of your investigation will be when you look at this. Can you tell me briefly when this will happen? For which case this will be true? Yeah, it's true. Actually, here it is. That's the one. Because omega 1 was the solution to this equation, n, for instance, will do. In fact, because I chose my omega 1 to be the very first non-trivial solution, your k, your k must be a multiple of n. And I think that there is an equivalent sign somewhere here. And that finally finishes the solution. So the answer to this question will be that this unknown expression A, it is 0 when k is what? Not a multiple of n. Yes, when k is not multiple of n, this will be 0. When k is multiple of n, this expression will be n. Because each of these omega's solution to this, when your k is multiple of n, when you raise your omegas to the power n, each of them will spit out 1. You add up n of identities, f of units, it's n. And that's where the question finishes.